Thanks.
Thank you very much, Debbie, and excited to be here. I am pinch hitting for Abe Ellis, who unfortunately couldn't make it to the event, but really happy to be here with this great panel of folks, and happy to be talking about DERs and their integration for T&D services. It's something I focus on a lot in my day job, and we've got a great panel to discuss quite a bit of the nuances of that. We are going to be having a bit of a fireside chat type of format for you. So each of the speakers is going to give a 10-minute kind of overview of their perspectives on this topic space. And then we've got some structured questions followed by about a half hour or so of audience Q&A. So please be noting your questions and be prepared to have some discussion following that. All right, so let's jump right in. Our panelists today are Arushi Sharma Frank, who's the founder and principal at Luminary Strategies, Darren Murtaugh, who's director of electric distribution strategy for ICF, Jennifer Schilling, who's VP of grid modernization at Eversource, and Astrid Atkinson, who's founder and CEO of Camus. And Arushi, why don't you lead us off?
Thank you. And you'll do the slides for me, or Obadiah, would you like me to?
Oh, yep.
Yank on those. Perfect. Okay, good morning. So immediately prior to my current role, let me through the right direction here. My job, among other things, at Tesla was to start the energy business in full force in the US, and that included starting the aggregated DER program in Texas, working on VPP in Puerto Rico, enabling and supporting Tesla's participation in programs, including those of some of my colleagues on the stage here, including the SMUD program, as well as Connected Solutions and its derivatives managed by Jennifer and her team and others, and Eversource's service territories in Massachusetts and Connecticut. And what I find really interesting that I'm going to focus on is in my role to kind of lead off this group of very experienced folks all tackling the T&D value proposition from different angles, is to tell you like what has really happened. So I started this work in 2020, and in that time frame, a few really big trends that kind of merge with a lot of what you're hearing now and what is informing my work now is finding that most of the early seed challenges on valuation and ascribing value to flexibility and asset valuation on the T&D system in the DER world is a lot of what I do now with large loads too. 4 years ago, I was sitting at a desk with Tesla's, SCED engineering and autobidder team saying, like, okay, we can export power in Texas from batteries, and we can participate in these specific programs. What are they? And right now, there are chief data scientists from Google backing startups I work with building load flexibility software for compute, asking me the exact same questions. And what I think is good about this session now, and what's good about having the large load conversation, is that I think it will accelerate the T&D flexibility and support conversation for small DERs. In the morning session, if you didn't get to make it, we heard from Michael Lee, Allison Silverstein, Beth Garza, Angela Long, and a colleague from Brattle, whose name I'm missing, but she did the Evolve study in Texas. And they were talking about exactly this, like what is the transmission and distribution value of all these DERs? People buy technology because they already have assigned a value of lost load or a value of resilience or a value of convenience to their purchase, right? It's a revealed preference. Now we're trying to take the value of assets that people have acquired for their own use and their resilience and trying to monetize them for a system that is beleaguered by CapEx, grid overbuild, confusion, low visibility on the distribution grid, and trying to make it all work together, right? And we're doing it in multiple regulated models around the country, dereg markets here in Texas, except for the NOEs. Then you have RA in California. You have islanded grids like HECO that have moved really far on T&D programs for DERs. And I think that is where we are with our industry, but it's really confusing. And it's in across 50 states. You can imagine my job trying to manage these programs in several jurisdictions. It takes some sort of unification and interest. And I truly believe that it is legacy utilities, utilities with load serving entity capacities, programs like SMUD, programs like the one run in Eversource, that will really help change the model, because at least we get first line of sight and unified line of sight across the different potential value streams. So if you've got power walls and cyber trucks in a neighborhood, whose job is it to monitor the impacts of those resources on a cul-de-sac and on the 3 single-phase transformers in that neighborhood? The individual aggregator's job isn't to do that. It's the utility's job. It's who's sending the bill. And I think that's where the conversation needs to land, is we have to acknowledge the limitations and the advantages of the systems we have to build the best programs. Let's see, got 6 minutes here. It's great. Let's see, this is really important. So if you went to the morning panel, you learned about the aggregated DER program. I want to tell you where it came from and how we got to ADER in Texas. Governor Newsom in California in 2021 was experiencing what was called a state level emergency. An emergency directive came out saying, if we have any batteries on the system that can discharge their power during our emergencies and help stabilize local distribution grids during our PSPS events, we would like them to run. My colleague at Tesla, Damon Franz, who recently left the company, said, like, well, you know, he's talking to the governor's office, like, well, you're not paying my customers to send their energy to the grid. There's no program to compensate them. They came up with an emergency way to compensate power walls in the emergency load reduction program operated by CAISO in conjunction with the CPUC, effectively overnight, so that power walls could provide capacity to the system. It was formalized the next year in a demand side program in the LRP program, which is now DSGS in California. But the momentum where we were able to show that our ability to reserve and then produce a output from power walls in response to a dispatch signal was something already being done in Australia for several years in the VPP demo and AMO. Then it came to California as a compensated model in the middle of the summer wildfire experience. And right around that time, Winter Storm Uri also hit Texas in February of 2021. That is what launched my past capacity to ask a bunch of voluntary Powerwall customers to just show up in a demo structure, follow a SCAD signal being received at one of our large battery sites, and perform RRS regulation, dispatch and SCAD, real-time telemetry, and provide the exact precise response as a large front of the meter corrected battery in aggregate and monitored all the way down to the individual device level. We, through the support of the PUC, got that program stood up so fast. It was the first place in the country that Secretary Granholm came to visit. That's what this photo is. That's why it's important to ask how the heck we did it so fast. And the funny thing about in getting a federal regulator to Texas to talk about energy programs is that they don't have any jurisdictional control or nexus. But here we are today, and Texas is a leader in DOE speak. If you talk to either this administration or the prior ones, Texas is a leader. And if you go right now to hearings being led by Senator Lummis and others on large load integration, et cetera, and interconnection and connect and manage and this and that, every single flyer that I'm seeing being passed around in Dirksen in the Senate has something about Texas on there and what works about their system and how do we replicate it in like Nevada. Which is crazy, but it also shows you how far we've come and how much dynamism I've seen in this industry. I don't think I could count a single senator 4 years ago who knew what the heck ERCOT was. Now they all know. And that's why I'm very happy to see the large load show up in this conversation on flexibility, because I think it's going to drive awareness and value creation on all sides. Some of the things that my colleagues are going to cover, I think, are here: recent learnings, programs with potential, things that we're hearing and seeing. But in my 2 minutes, I'm going to go to a couple of the big problems that I have started to see that need to kind of get fleshed out on just the distribution system itself. You know, Michael Lee mentioned one of them this morning, is that we don't have a ton of visibility on the distribution system. In most cases, we don't know whether transformers are over or underloading on an inter-hour basis. And in most cases, we also don't have the resources to roll out trucks to check on them regularly. This was a big problem in islanded utilities like Luma, where they're just trying to avoid the truck roll. It's like, well, okay, we don't know what's happening on the transformer. It's like, okay, well then those transformers, sometimes they blow up, melt down, et cetera. And then you have bigger problems. I've learned in the past year in particular, working more with utilities directly, that size really matters with how they handle the distribution level challenges. With some smaller utilities, there's faster implementation. of low voltage awareness, just smaller, they're leaner, they're more flexible. So being kind of like fragmented or balkanized, as we call our grid operations sometimes, can be an advantage for getting DER evaluation right for distribution grids. Islanded grids and smaller grids present a more feasible and workable handling friendly approach for a lot of utilities. And one of the reasons I dragged Astrid to join is that I was really impressed with the study Camus is doing with the Vermont Electric Cooperative, which I think you might hear about. With the larger utilities, I think the cyclical pressures are really tough. I also represent now, having left Tesla, private equity interest in acquisition on all sorts of small tech companies that are designed to support utilities in managing their distribution systems. And the repeated theme is like, how will we get out of our cyclical pains by implementing this type of technology? And when you talk to utilities now about DERs and their value in the T&D system, what I tell anyone in this business is go to CFOs and describe the value proposition that helps them get out of the cyclical pressures they're in, where CapEx is pressured, the cost of debt is under pressure, their ratings are pressured, their rate base is pressured, and their regulators don't really like them, right? And you have to go up to the top. And I also say, like, when I was at Tesla, I was able to sit down with anyone I wanted at a utility and talk to them because it was like, oh, it's Elon's company, let's talk. But that can't be the only reason that we get in front of utility executives to have these conversations. And so I encourage startups, engineering firms, anyone that's working on these problems to figure out a path to CFOs and move the conversation forward from the place where it really makes sense in the business model that you're trying to fit this valuation approach into. Okay, so with that, I'll turn it over to our next speaker. Who is this way? Darren.
There we go. Okay. Well, good morning, good afternoon, everybody. Darren Murtaugh with ICF. I lead our distribution strategy practice. And I want to talk a little bit today. So much of what we do really does revolve around distributed energy resources and specifically integrating them into utility planning and operations in order to optimize that grid value that they can contribute. And why is this important to me? Well, I start by recognizing a trend that we're seeing in the industry. If you look at this graph on the right-hand side, this is utility capital investment in distribution systems. The orange line on the bottom is what that investment would look like if it simply followed the pace of inflation. But the blue line on top is what the actual investment in the distribution system has been. And you note that since 2013, a steep uptick in that investment over time, up to the point where today, total investment in the distribution system represents about 44% of overall utility capital expenditures on average. That's far cry from what it was earlier in my career. And in a lot of ways, I think warranted. The utilities, we are facing a lot more uncertainty today than we ever had to contend with in the past. And that uncertainty shows up in a number of different ways. I highlight here the pie chart on your left. We've got where the distribution investments are allocated. We have your replacement costs. How long has the grid been up and running? Give or take 130-ish years. Long time. Has the replacement strategy kept up? In a lot of cases, no, not necessarily. So we do have aging infrastructure that's putting pressure on the system. That aging infrastructure introduces uncertainty about unplanned outages as equipment begins to age out. We also have system expansion. Load growth can be a very good thing. And what we're recognizing is the nature of that load growth is a little bit different than what we've seen in the past, specifically with electrification. Both electric vehicles and electrification more broadly. How much, how fast, where will it show up? We certainly don't want to be a deterrent or a barrier to customers adopting the technologies that they want. So we want to be ahead of the curve, but not too far. Hardening, and unfortunately it doesn't look like the slide came through here, but 28% shows up in hardening and resilience. This is a conversation that I don't remember having back in 2003, but we talk a lot about resiliency today. Why? Well, major storms, wildfires, other major events, they're happening with a greater frequency, with a greater duration than what we've experienced in the past, and with a greater impact. And so a fair amount of investment going into hardening and resiliency. And then finally, the distributed energy resources, challenging the traditional way that the grid was originally designed. Do we have the level of visibility deep into the distribution system to uphold that reliability, understanding that it is and will continue to be a far more dynamic operation? All of this adds upward pressure to the need to invest in the distribution system. That results in upward pressure on rates. And if we follow this blue trend line forward, my fear, my worry is that it quickly becomes untenable. Not only the rate impact, but let alone, can you build fast enough to get ahead of the curve? I'm not sure that you can. I do believe strongly that we need to supplement this strategy. We need to find a way to use the value that DER can contribute to the distribution system. We do have one client that we're working with who has a hypothesis, and their hypothesis is that a portfolio of DERs properly coordinated would be better at meeting a grid need and be more cost effective. And I tend to share that hypothesis, and I know we're not alone. When you look across the industry, these states in green here, these are areas where there are active pursuits of using DER, or at least investigating the use of DER for distribution grid services. So what is our approach here? Well, I think the first boogeyman to call out, and myself being a distribution planner, transmission and distribution planner originally, the first question that I'm going to ask is, yeah, I understand that in theory, DER can contribute value, but it needs to be dependable. I'm not going to change the way I plan, design, and operate the grid if I can't count on the resource. Is it going to be there when I call on it? And when I call on it, is the performance going to be what I need the performance to be? Will 1 megawatt of thermostats on a distribution feeder, does that translate to 1 megawatt of distribution capacity offset? Probably not. But what is the answer? And in order to answer that, it opens more questions than it does answers. I need to wonder, well, what time of day are we talking about? What season are we talking about? And is this something that I want to dispatch every single day to manage the peak load? Or is this only on occasion following an unplanned feeder outage with no notice? All of this factors in to what the efficacy of that program is likely to be, let alone how can I look across various DERs, disparate program types, and have them each showing up in the capacity needed for the duration needed to deliver on a specific defined distribution value, meeting my performance characteristics that I want to see as a planner? That's what we refer to as the operational potential of DER. It is a fraction of that enrolled capacity. It is the fraction that represents the dependable capacity that you can use and rely upon for distribution services. And to illustrate this is one example of how this could show up. I'm showing an orchestrated dispatch, 24-hour load shape, with a peak load management use case, trying to manage this feeder's load to no more than 10 megawatts. That is the limitation. We have a collection of resources under the base dispatch. We have a supplemental dispatch and a reserve dispatch. They all have different characteristics, different attributes. I only highlight a couple of them on this slide for illustration. But the idea here, the point, is having each of them show up in the capacity needed for the durations needed to be able to reliably manage the distribution constraint. The question is, how does this translate then to actual value for the distribution system? And that's where I will hand it to my colleague, Jennifer.
All right, good morning. Jen Schilling, I am the Vice President for Grid Modernization at Eversource. Yeah. And for those of you not familiar with Eversource, we are New England's largest energy provider, serving close to 4 million customers across New Hampshire, Massachusetts, and Connecticut. Okay, so when we think about the sources of value, it matters what types of use cases that you're dispatching for. I'm going to focus, for the sake of time, on the 3 to the right of the slide here. So the first case is, we call it bridge to wires, right? I'm building a substation, I'm building a feeder, and it's going to take me some time. I got to site it, I got to permit it, I got to procure the equipment, which a lot of it is long lead. And the load is growing so quickly. So this is in a dynamic in our area. We got electrification, and we have other needs on the system. So load is growing and I need something now. I value that very highly. And a lot of the sources of value for that is, if I am worried that my capacity isn't sufficient to meet the load, I have to roll a generator, I have to move my system around, I have to move system around on the load, which creates a lot of reliability risk. These are the sources of value of bridge to wires. I am going to build the infrastructure, I just need something to be a bridge until the infrastructure is in place. So that's one. The second is the one probably most people are familiar with, and we call it deferral value, right? Again, load is growing. I need capacity. DER is growing. I'm worried about reverse flow back onto the transmission system. These things are happening. We know they're happening. We project them. At Eversource, we project, we have plans. Darren's slide is exactly correct, right? We have a lot of needs on the system. So, but what if I was able to dispatch distributed energy resources in a coordinated fashion, similar to the chart that Darren showed. And that means that what I needed to build in 2030, I can maybe push it off and build it in 2032. So now I've created value. That's the time value of money, something that was very expensive that I needed to build in 2032. I can wait until 2034. That creates a value. The third is one that probably most people in the room are familiar with. This is kind of the more near-term use case, which is flexible interconnections. So we have queues like you would not believe. There's so many resources that are trying to interconnect to the system, and it creates cost. We have to make sure that the system is available and reliable to accommodate, create that path to market for the DER facilities. So what if I could dispatch you such that you're not creating that reverse flow in the times of the year? So think about the light load periods, maybe the spring and the fall. I got limited load and I have a lot of sun, so I'm exporting onto the system. I'm creating an overload in the reverse direction. If I could say, hey, maybe if you don't export quite as much just in those periods of time, what would have cost $10 million for the substation upgrade to interconnect, I can do for 2. That creates value. So we know that the ability to utilize distributed energy resources creates monetary value on the system. We can monetize it. To date, in our service territory, we dispatch for ISO system peak. So we know that has value, that we turn that into dollars, and that turns into programs where I'm dispatching for ISO system peak. What we're talking about here is now I have a local need. I have a need at a substation. I have a need at a feeder, and I can take those resources and I can dispatch them for the specific use case and create those sources of value. So I'm going to anticipate a question I'm probably going to get, and I'll just go ahead and answer it. Hey, don't you make money by building substations? Why would you not want to build a substation? Was that anybody thinking that question? Probably. Very true, very true. And, I think the reality is we all know that with data centers with growing load, the needs on the system, we have to think differently about how it's all the tools in the toolbox, right? We know New England is some of the most expensive electricity in the country. And we know that this is not sustainable. We have a high percentage of our customers on some sort of discounted rate, right? The pressures of resiliency, of aging infrastructure, electrification, data centers, and load growth, we cannot live in the old world where there was only one model, right? We all benefit. We all benefit from meeting the needs in the most cost-effective way possible. We've been, as a utility for years and years and years, building things as cost effectively as possible to meet our needs. This is just an evolution of that. So we are looking for how can we bring these resources to bear? How can we make them part of the solution? It's all in, right? I need to build and I need to dispatch. I need all of these things to work in concert. So that was my main point. So like I said, lots of value, different places. Now, we're probably not going to have time here to talk about the technology, but I will make a pitch for, I think it came up, some of the bigger utilities, right? It does take time. And one of the things, so it's not just my ability to come up with a program and say, hey, I've created $10 million worth of value. I'm gonna share that value with you, customer or DER facilitator. It also takes the technology to work. And that's something that we at Eversource are working hard to do, because what it really takes to be able to do this, and I think we're going to talk about, I need visibility, right? I need to be able to see where these resources are in real time. That's the important part, right? I'm an operator, I'm keeping the lights on, I'm managing power flow on the system. I need to be able to see that my load is creeping up on the substation and I need to do something. What resources are available to me? Well, not just the generator or the switching load we talked about before, but aggregated distributed energy resources. What's available to me? Maybe I can back down an EV charger. Maybe I can dispatch some Wi-Fi thermostats. Maybe I have a standalone battery that is available to me. What's available? I need to see it. I need to be able to send a signal to it and say, hey, we need you right now. I need to see that it responded, and I need to see that the constraint was alleviated. So I need visibility, and I do need the ability to be able to have communication and control with those facilities. So there's a technology angle to this as well, but together, none of this works. I can create all this fancy technology, communication, and control, but if I don't have the resources available to be that tool in the toolbox, I will not have this is not a feasible solution. And to do that, we really do need to work on the valuation angle. We need to make sure that we're not overpaying or underpaying and get that balance right. So I think that's the end of me. I'm going to hand it over.
Awesome. Well, I'm going to pick it up approximately right where you left off and talk just a little bit about a couple of concrete examples that look at, firstly, large scale visibility, both as a planning study, but then also in real time. Secondly, a concrete example of a utility program where we've been working with the utility to provide distribution deferral services at the transformer level. And then I want to kind of close by touching on an example of doing this with larger loads, because when you're thinking about bang for buck, larger loads have more bang and also more buck. So a couple things. Firstly, just to quickly intro the technology role that we typically play with utilities that we work with. The Camus platform really at its heart is a large-scale data integration platform that brings together utility data from across traditional sources like SCADA, GIS, AMI, et cetera, but also from third parties where available to provide that level of integrated visibility that can actually help to answer questions around like, you know, what is the load on this substation? How is that growing over time? What is the DER presence on the substation? What services could it contribute? What is it doing? And that's something that most utilities don't really have a strong need for in real time today, or at least they haven't, and that's changing really quickly. And so a couple of examples that I'm going to talk about here are, these are all real world examples from utilities that we've worked with. But it really starts with that data. And one thing that I just really want to highlight from a technology and a data perspective before we go ahead and dig into case studies on that is that that data is out there. This isn't a case where we need to go and re-instrument our grids to, add visibility that isn't present. This isn't, a sort of 10-year, like go back and redo the whole thing. Most utilities have some form of AMI deployment today. Most utilities have some form of updated SCADA. Most utilities now have digital GIS maps. Those are their foundational components. The tricky part is typically putting them together in the same place. And that's still really challenging for most utilities that we talk to and work with. Because even though utilities have made a lot of investments in infrastructure around things like ADMS systems and DERM systems and so forth, the ADMS typically incorporates data from GIS and from SCADA, but doesn't tell you very much about what's happening with customer loads or small loads located on the grid. It may include large ones. Most utilities have AMI, but that data isn't available in the same places or the same ways as the core system data. And that just makes it hard to get that visibility and understand what's out there. So I want to talk first about one example, which is actually a planning example. And this is a published case study that we did with AES Indiana. And the question that they had was, with current electrification trends in their territory on their actual grid, basically, how long will it be before they have to upgrade every single grid component, and what will that cost? So this study looked specifically at load growth from EVs. There's no reason it can't incorporate other things, but this was the specific question that they had, was really just looking at this one example of like, okay, given what we know about EV adoption in our territory today, this is derived from AMI data, and what we know about basically demographic trends about EV adoption, what will be the timeline to upgrade, and then the distribution costs as a result of EV adoption within this territory. And then what would be the impact of different ways of managing that. So what we found, which was consistent with having run this analysis with other utilities as well, was that the level of EV adoption that's required to drive pretty significant distribution upgrade costs is very low. It's actually only about 3 to 5% of customers adopting EVs that's required to start generating the sorts of radical cost increases on the distribution side that we saw in the previous slide, that's sort of showing the very much up and to the right. And the reason for that is that most utility upgrade cycles are driven by peak loads. And EVs tend to cluster. And this happens in different ways for different load types. But what you tend to see is that while overall impact is relatively low, if you just kind of peanut butter EV adoption stats over the grid as a whole, if you take the actual adoption that exists today and then you grow it, and you look at that in a growth trajectory that is more likely to actually happen in the world, what you see is that the small number of highly loaded feeders and transformers start to see peaks quite early. And that tends to drive the upgrade costs and makes them substantially higher than they would otherwise have been planned to be. So for AES Indiana, we found that it was about $50 million of unplanned distribution upgrade costs within the next 5 years, and that they were going to reach a tipping point on significant increase in distribution costs around 2028, between about 3 and 5% of overall territory adoption. We modeled multiple interventions to understand how would you avoid that? Or how could you defer these costs? What's the opportunity for distribution deferrals by managing these EVs as they get added? And we looked at 3 different scenarios. One was time of use rates. One was basically a version of sort of monitor. I like to think of it as like data as a non-wires alternative. It's basically, what if you had visibility and you could just make less conservative planning assumptions? And then the last one was looking at managed charging programs, where we actually like cap the behavior of these EVs in the windows of time where they generate peaks. And what we found was that, firstly, time of use rates make it substantially worse. And the reason for that is that, as I mentioned, distribution upgrade costs are driven by peaks. Time of use rates create peaks that didn't previously exist in the organic charging behavior, where people might plug in at any number of times throughout the day. So as you put a time of use rate in place, you're encouraging customers to plug in at certain times. And so very quickly, that actually makes the grid impact quite a bit worse. Managed charging is the best intervention in the sense that it can help to defer upgrades for periods of many years in many cases. So you can go from like maybe looking at a period of perhaps it's 2 or 3 years to upgrading a transformer to maybe 8 or 10. And that involves basically being able to cap charging behavior at the distribution transformer level for every vehicle. But in between and substantially cheaper is observing these sites and making less conservative planning assumptions, because actually the level of charging coincidence is fairly low in terms of how people actually plug in and actually charge. And so, one thing that we looked at with this utility was basically like, if they assume a 40% coincidence, that drives a certain set of assumptions around distribution time to upgrade. If you assume a 20% coincidence, that's actually a lot longer time. The key is that in order to make that safe, you need to be able to see what's happening and see when those trends are really adding up. And so that kind of goes into the second case study that I want to talk about quickly, which is looking at actually doing managed charging program in the field with a real utility. So this is with Vermont Electric Cooperative. They too have published results around this. And we ran a version of the study first that we did with AES to understand like what actually is the exposure to increased transformer upgrade requirements from EV adoption in their territory. And as with AES Indiana, we found that particularly with the introduction of time of use rates or market rates, they have a subset of feeders and transformers where increased coincidence of charging will drive an accelerated upgrade cycle, particularly for transformers. And they wanted to look at ways to avoid that. So this deployment actually uses a sampling of transformer level sensors in addition to transformer data aggregated from AMI. And that's because this utility has relatively coarse-grained AMI data. But it's a nice example of where like adding some instrumentation can really add a lot of value and a lot of confidence to this. But so they have that in place. And then we also aggregate information about transformer load in pseudo real time for every transformer on an ongoing basis. And then we use that to forecast the load for every transformer over a 2-day look ahead. And we calculate a distribution envelope, basically a capacity envelope for every EV that's located behind those. That then gets communicated to the EV charger, and the EV charger knows that it needs to curtail at certain times. This is using a charge point program. One of the big challenges, which perhaps we can get to in the questions, is program sign up and compliance. But in the case of a charge point program where all of the chargers are like known and controlled, that's something that's relatively practical. And so this is something that the utility is in fact seeing the distribution deferral value and transformer impact value that they wanted to. And they're looking to roll that out as a default across their whole territory. They pay a little bit of money to their customers for signing up, but the benefit is huge in terms of system costs and is more than worth it in this particular case. So with not very much time left, I also just wanted to kind of shout out to looking at the same kinds of programs. Oh, this is looking at the envelope, shipping the envelope to the specific charger. Looking at the same kind of programs applied to larger loads. And this is important because, as Arushi mentioned, like those can really drive a lot of costs in terms of upgrade, either to the customer or to all of the customers that are clients of the utility, depending on how costs are shared. And also the most practical time to get flexibility added to the system is at the time when the asset that's driving the need is connected. And so, that might be when an EV is bought and connected, plugged in and charged, just with VEC, but it also could be at the point where you're discussing a flexible interconnection or a bridge to wires type program. And you're going through the process of getting it plugged in. That's a great point to ask, like, hey, I need a certain amount of flexibility. I can provide you with a financial incentive to do that. And for larger loads, that looks typically like lesser upgrade costs associated with the interconnection. It's a really good case study from a partner of ours. It's not one of ours in Australia that talks about this. that I can provide links to, maybe with the slides after this, but looking at just a case study of doing this with an EV bus fleet charging location, where they kind of started with the assumption of needing a $6 million upgrade for the substation in an urban area where the fleet was going to get connected. What they did was put sensors to look at impact of that fleet load on the grid around it, and had an agreement with the fleet that they were going to stay below a certain cap over a certain period of time while the upgrade was put in place. So it's kind of a bridge to wires model. And what they found was that they actually didn't really need to do the upgrade as planned. When they could monitor it and when the site could provide a certain amount of curtailment, they ended up getting away with like a $400,000 upgrade instead. Didn't have to dig up the road, didn't have to fully upgrade the substation, just upgraded, I think it was a transformer and some conductors. And it's just a really nice concrete example of the kinds of savings that are available if you can see what's out there and if you can have a conversation at the time of interconnection. And also, I think lastly, talks about the value of DERs, not just to small and resi ones, but also larger fleet and CNI type loads, which, as mentioned, has both, more bang and more buck available to work with. So I'll leave it there because I'm well over time, but happy to provide links and answer questions.